start this lecture with a thought process that question can never be silly, it can be a beautiful lily in the garden of knowledge, that is the truth age after age. And when you were, all of you were, in your baby stage, you were asking too many questions, but as you are growing, you are not asking any question. So that is the hard truth of life, but it is very important to have questions. So let us, talk about thermodynamics today and work. Before that, let us recall what we learned in the last lecture. We basically looked at the equilibrium and various kinds of equilibrium, and a thermodynamic system can attain equilibrium only when it can attain thermal, mechanical, and what you call chemical equilibrium, also the phase equilibrium. And then we looked at the what you call stability of the equilibrium process, and four kind of situation we look at: the stable, unstable, metastable, and neutral stable. And we will be most of the time discussing about the stable equilibrium position kind of concept. But however, in case of phase changes and other thing, we may invoke the metastable conditions. And beside this, we learned a very important concept which is very essential for the classical thermodynamic, that is a quasi-static process or a quasi-equilibrium process. So now we will be looking at the thermodynamic concept of work, because if you look at the thermodynamic system can interact with its surrounding only two ways. One is the work interaction, other is the heat interactions. First we will consider the work interaction. And work interaction, if you look at, we will take our as usual piston cylinder arrangement, which will be containing certain amount of gas, and which will be having like a system here, let's say, kind of things to start with, and which is balanced by this force. And if this is being what you call reduced by delta F, this force whatever acting, then the piston, earlier it was here with this, and then its system boundary will increase. This is a what you call movable boundary, right? And there is a displacement ds. So if you look at mechanics from point of view, right, it is basically the force into displacement, right? As a result, the volume, like you are at the state 1 here, and as you go on decreasing the force, and there will be increase in volume of the gases in the system, and it will be reaching a steady state, another state 2, right? And all the time you can think of that it is attaining the quasi equilibrium, because you are changing the what you call the force by a very very small amount, such that it will attaining the mechanical equilibrium. And one can also consider it as a reversible process, because it is a very slow, and there is no friction between the cylinder and piston or any other kind, which will be won't really allow the system to move reversibly, right? Or in other words, it will be make it process irreversible. So if you look at from the mechanics point of view, the work done will be what? If I take this tiny strip here, right, and that is nothing but your displacement, like and if you look at this displacement, piston has moved through distance ds, and force and ds, and force is acting, so that the force is acting with the pressure P, because from the system, and then this is the surface area, so it becomes PA and ds, and this what you call change in volume, A and ds is nothing but change in volume. And if you integrate this thing between the state 1 and to 2, you will get PdV, right? And so if you look at, for this to integrate, what you need, you should know the relationship between the pressure and volume, right? Isn't it? Then only you can integrate. Otherwise, if the pressure is remaining constant, what will happen? Then you can find out what is the change in volume, and then you can do the work. But however, and that is possible only for what? Isobaric process, right? Where the pressure is remaining constant, only the change in volume, right? But for other processes, you should know the relations between the pressure and volume. And if you look at this integral, is basically this area, that will give me the work done. That means this area will give me, if I integrate, will give me P and V diagram, that is in the plot PV diagram, it will give me this area, will give me the work done, and which can be expressed in the kilojoule. Now, if you look at during this process, right, is it the work is possessed by the system or not? See, if you look at the unit of the work is kilojoule or joule, whatever you call, right? But that is the unit of energy. Am I right or wrong? Yes or no? Is a energy. So, is it work is same as energy? Energy is possessed by the system, okay? Or if there is a interaction between system and surrounding, there will be change in energy. But is it there will be change in work also of the system? Actually, it is not. Basically, work is done by expending the energy. Okay, work is done by expending or by using the energy, right? But the work is basically not the energy, it is the energy in transit. During the process it occurs. That means it is a basically boundary phenomenon. If you look at this way, piston, piston is moving, right? If it is not moving, because that is the boundary, like if you look at this is a system boundary changing, right? Earlier it was started with this, and then after the displacement it has moved to distance, So therefore the work, we call it as a boundary phenomena kind of things. So, and it will be dependent on, like let's say if it is it is going from station 1 to it is going to the station 2, it can go through path A, it can go through path B, and it can go through path C, right? The work, right? It can occur. And if it is taking different path, the work done will be different. For example, the path, if it will take the path A, it will be 10 kilojoule. If it is path B, it will be 8 kilojoule. And if it is path C, it will be something 5 kilojoule in this example, right? And then that means the work is basically dependent on the path. So therefore, work done can be considered as a path function. It is not a point function. Whereas energy is basically what? Is a point function. Therefore, the work is not a property of the system because it is dependent on the path. Whereas the energy is stored in a system but not the work. Work cannot be possessed by the system. Okay, but whereas energy can be possessed by the system. So therefore, we call work is energy in transit, can be identified or can be manifested, only when system undergoes a process. If there is no interaction between the system and surrounding, right, okay, then work done will be what? Will be zero, right? So, therefore, one has to understand the difference between work and energy. Let us take an example. like a piston cylinder device initially uh, contains 0.4 meter cube of air at 100 kPa at 80 degrees Celsius. That means, if you look at volume is given to you, pressure is given to you, so also the temperature. Air is compressed, right, to 0.1 meter cube in such a way that temperature inside cylinder remaining constant. This is basically isothermal process, temperature remaining constant. And we need to determine the work done during this process, right. So let us consider these are our system boundary, right, is a piston cylinder arrangement and air and 100 kPa and initial volume is 0.4 meter cube and temperature is 80 degrees Celsius, right. And we will it will be station here at this point and it will be compressed. That means we will be putting some weight here so that it will be compressed such that pressure of the system will be attaining a higher pressure with and it is a quasi-static process we are assuming. So the process will go on in this direction such that it is attain the state 2 at which the volume is 0.1 meter cube. Let us say by that piston may be moving through this process. This is your station 2. Right. So we need to find out basically work done. So these are the things are given, like V1 is given 0.4 meter cube, V2 is given 1 meter cube and P1 is given 100 kPa and temperature 80 degrees Celsius. So what we will do, we can apply the ideal gas law. We know that PV is equal to mRT and this R is basically specific gas constant here, and if you look at if temperature is remaining constant, then what will happen to this term? This is mass is remaining constant inside the system. So therefore this term is basically a constant C. So therefore we get a relationship between P and V, right. P is equal to C by V. And if we take this thing that work done is equal to P dV 1 to 2, then you can put this relationship between the P and V here and you integrate it, and we know that C is nothing but your P1 V1, right, and the V2, V1, you put this thing to put all the numbers whatever is there, and then you will get the work done is equal to 55.45 kilojoule, right. So now this is coming with a negative sign. What is the meaning of that? That means what? Who is doing work here, system or surrounding? It is the surrounding that is doing the work on the system, right. Are you getting? If the system will be doing work, then it will be positive. That means this is basically a compression work, and if it is expanded, that means piston will move. If instead of from station 2 to station 1, if you come back, right, it need not to take the same path, okay. It may take path if it is reversible, right. If it is irreversible, it need not to take the same path. Suppose I am here, I will have to go to this, then what will happen? Work done will be positive. Suppose I am at station 2 and I am I will be coming to the station 1 following the same path, then I will get the same work done 55.45 kilojoule but with a positive sign. That means the work is done by the system on its surrounding. Is that clear? Okay. So now let us take a situation in which work is not equal to PD, because we have seen this is the PdV work, okay. But we can consider a situation where PDV is not there in picture. Let us say we will consider a free expansion. One example, I will be taking few example for that. Let us say that there is a two chambers, right. The chamber 1 contains gas at P1 V1, and in a chamber 2 is a vacuum. Now there is a partition here, I can remove this partition, okay, and the pressure here is vacuum. So what will be the work done? Let us do in another way. For example, what I will say, I will place several partitions here. These are all partitions, right? I will remove this partition, first partition. Then what will happen? The volume became this V1 plus VA1. This is your chamber 2, okay, VA1. This is became new volume, okay. Then what will happen? The pressure will change, am I right? Because the gas is same in the system, right, and this system becoming like that, for here. Earlier it was in this chamber 1 and it became increased, so that pressure will be what you call reducing, am I right? So you can think of the pressure is here, one here, and when this, if the partition is removed here, and then you will go to the point A, right, you can get. And similarly another partition is being removed here, this is being removed, right, you will get B and C, D, like that, all the partition you will be removing, and you can come up to a point known as point 2, right. You can say, look, I will take this area, right, and say that this is the what you call work done in a PDV sense, right. Is it true or not? Is it true or not? Actually it cannot be. That's why, that is the reason, like I have put into this dashed line just to indicate that it is not a reversible process, okay. That is one thing. Generally when you draw a process diagram in thermodynamic, particularly classical thermodynamic, we use a solid line if it is a process, a reversible process, and irreversible process we use the dashed line. That convention you should keep in mind. And but important point is there, the work done will be not corresponding to this area what I have shown, or okay. Why? Because the work done will be in this case what? What will be work done? Work done will be 0, because the expansion of gas is not restrained by equal but opposite force at the moving boundary, because all the time it is 0 pressure, right, is experiencing. So therefore it is not, cannot be as such. And no external force is moving through a distance, as such, because the vacuum is remaining there. So free expansion is basically work, free expansion work or work done due to the free expansion will be 0. So let us consider another example, that is the paddle wheel, right. What we will do, we will consider again a piston cylinder arrangement, right, but however this piston movement is being latched. Latch means it is fixed, okay, is fixed, that means it is not moving. So I will take this as my system. This is the dashed line I have put, and there is a paddle wheel which is rotating, it is like a fan you are putting, okay. And then I can think of using joining with this pulleys to a mass, and then mass is going down, right. So if it will go down and it is subjected to gravity, what will happen, right, what will happen? There will be change in some kind of potential energy. Okay, but however, when it is rotating here with some omega in what you call some RPM or the angular velocity omega, then like there is no change in the fixed boundary. That means there is no PdV work, there is no change in volume, right. That means, can you say that work done will be 0? Am I right or wrong? Work done will be 0 or not, or will it be finite? Actually, it will be definitely finite, because there is as I told earlier, this mass is changing its position, going downwards, so therefore there will be decrease in potential energy mass. That means work is done on the gas. If I consider here as the in the system we call it as a gas, so therefore the work done will be equal to that whatever the change in potential energy. Keep in mind that this work done in only in the one direction. Suppose what will happen, I will change this position, like mass from the lower to the higher height. What will happen? It won't, right? And what will happen? It may be rotated in the opposite direction. That's all we can do, right? Okay, but however it will be not reversible, and then that work done in case of reversible process is not equal to PdV. However, for reversible process we call it as basically the PdV work, right. Let us take another example. This is storage battery, right. So we take this as my system, what you call, this is my system, and it is connected, the battery is connected to a resistance, right. This is the resistance, and with a switch, when I connect to that, this resistance will be what you call activated, and you can get some heat, and that means the system, if you look at, is doing some work on its surrounding. Surrounding means in this case it is the resistance, right. Now you understand like what I call surrounding. Can I say air as a surrounding? No. Is the resistance which is surrounding and which is acted upon by this system. So now I want to find out how much work is done by this. With the definition, that means force will be acting, it will be going through the displacement or PdV work. Can I do that? So in other words, let me ask, is there any work done by the battery? Of course it is being done. Am I right? Yes or no? Because otherwise how the resistance is going and we are getting some heating effects. If you can measure the temperature nearby resistance and then find out there is a change whenever the switch is on and battery is connected to the resistance, right. From the definition of work in mechanics, what we have discussed till now, in this case work done will be 0 from that definition. Why? Because there is no force which is moving through any distance. However, as I told, the system has interacted with its surrounding, that is the resistance. Hence, the definition of work from the mechanics, what we have seen, has a limitation, right. It is not really working for all the things and whatever we will be handling in thermodynamics, because the battery and other things, lot of non-PdV work can be handled by this thing. So therefore, we need to define the work in the thermodynamic sense, right. For that, let us consider again our piston cylinder arrangement, right, which contains the gas here, and this is my system, and if you look at, it is connected to a lever and a pulley with a mass m, and if this pressure is higher here and it may go up, and as a result the hinge, this will go down, and it will be, the mass will be, let us say, at instant Z1, and it is going to the Z2 distance, right. So then what will be the work done? What will be work done? Because this mass is moving through a gravitational force field. So therefore the change in potential energy is nothing but your mechanical work, that is F into Z2 minus Z1, this distance, right. And the F we know is the gravitational force, so m into g, mass of this weight, and g is the acceleration due to gravity, right. And this, from this what we can observe, can we redefine the definition of work what we had seen in the mechanics from this? So basically you can think of that the work is said to be done by a system on its surrounding, whose sole effect on its surrounding could be viewed as the raising of a mass through a distance against gravitational force, right. And this definition was historically given first by the M. Planck, which is one of the pioneer in thermodynamics, and developed later on by J. H. Cannon. And what is the meaning of this? Is it that we will be telling, like, look, it has to be always raising a mass through the distance against gravitational force? Certainly no. And what it says, that the thermodynamic work involves both the system and surrounding. It does not state that mass is actually raised by the application of a force, in this case gravitational force what we are talking about. It only states that the sole effect external to the system is to raise the mass through a distance against the gravitational pull, right. You can take this as a imagination and then put it, and then you can get the work done for all the system, including the PDV work. In other words, by for non-PDV work, this definition can work. Now what we will say, to illustrate this point further, we will take this again, the storage battery example. What we will do, instead of resistance, what earlier it was here, we will imagine that it is being connected, replaced by a motor, and then the motor is connected with a mass, and which is it can be raised to the gravitational field, right. And then you can fit into the definition of thermodynamic very well, right. So although it is not a PDV work, but however it is being fitted well in the definition of the thermodynamic work. So if you look at, like, when switch is on, motor runs and mass is raised. I have already explained this thing. In this case, external to the system, that is the system in this case is battery. Only effect is the raising of mass, hence the interaction is called the thermodynamic work. So keep in mind that no mass is raised through any distance against gravitational field. However, we are just saying that it is just a what you call adding this concept so that you can put into the what you call thermodynamic definition wise. So let us look at other work what we will be handling, work done on the elastic solid bars. So if you look at this solid bar which is subjected to a force, and it is having some cross sectional area which is not being shown here. Let us say this will be a cross sectional area, right, A, and when the force is applied, what will happen? That will be what you call elongated. And if you remove this force, what will happen? It will go back to the original position, provided it is in elastic region, right, in which Hooke's law will be valid. You must be knowing from your mechanics. right? And one way it is what you call reversible process, right? And one can also think of like as if the solid bar is behaving like a spring whenever the force is applied within the elastic range. Of course, in the plastic range, it cannot be. Am I right? So, therefore, if you look at the work done is basically the force into the displacement. If you look at, there will be the displacement, let's say dx, and this is nothing but your f dx. And what is the force? Force is basically, can be expressed in terms of what? Normal stress, because when this force is applied, this material will be trying to resist and it will develop a stress. And this force is perpendicular to the cross sectional area of the bar. So therefore, this is the normal stress, right? And you can integrate this thing and get the work done as such. So work associated with the stretching of a liquid film, let's say there is a what you call movable bar, and then you can of course with a rigid frame here, and if you dip this frame in the soap solution and you move this thing movable wire, and then you can what you call get a film, right, whenever you are applying certain force kind of things. And this film is formed due to your surface tension. Am I right? Surface tension. You might be thinking what you will do with this, like like your droplets are being formed due to the surface tension force, and so also the raindrops and other things, and you can use this film for the event flow visualization in fluid mechanics. So we need to now of course look at how much work is done by this example, like where the liquid film is being stretched by a force F. So that is basically surface work. I am like tension work, surface tension work will be sigma S into A, and this sigma S is basically surface tension force per unit length, right? That is being defined into dA. And what will be this dA here? If you look at this diagram, what will be dA? That will be, this is the length, let's say this is your x, right, and this is your b. What will be the change in length? And this is your dx. So what will be the change in A, dA? What it will be? It will be, see there are two surfaces there, one is here, another is other side, right? So therefore it will be 2, the change in area will be 2b into dx, right? That is the change, okay? And then you can integrate this and then get that work done as such. So let us look at some non-mechanical forms of work. Like for example, if you look at this reversible Daniell cell, of course nowadays people are talking about fuel cells and other things, which is a very hot topic. And let us look at this reversible Daniell cell, and which is having a copper electrode dipped into this solution copper sulfate, and zinc electrode dipped in this zinc sulfate, and with a membrane here, and it is connected to a potentiometer, and of course this is G is basically galvanometer, which is subjected to the voltage E, and it is in equilibrium, right? Let's say what will happen, like in the potentiometer you will reduce the voltage by a very tiny amount, okay? Then what will happen? That there is some charge will be flowing through this, and then some work will be done on that. And if we do the other way around, increase this voltage, and such that the more charge will be coming from here and current will be flowing through this, then will be work done by the surrounding on the system, if I consider that. So if you look at the work done will be nothing but E dz, where the dz is the quantity of charge transferred through the external circuit, like this is your external circuit, right? And this is basically non-mechanical forms of work. And there will be electrical work, right? Electrical work is basically being produced due to the EMF, that is the electric potential, or there is basically a force, and there will be a displacement. One can think of electrical charge will be moving, and then we can call it as basically what you call some kind of work we can really find it out. Similarly, the magnetic work is basically defined as the production of magnetic field strength and the total magnetic dipole moments. So there are various forms of work one can think of, and which we may deal with some time, but most of the time we will be working with the PDF work, right? And maybe some kind of situation we may look at the non-mechanical works kind of things, which is we can call it as a non-PDF work. So so various forms of work you may brush it up and see that. Let us now we generalize by considering various modes of work. We have taken here compression and expansion, that we have seen, that is in the from the mechanics point of view, and then pressure, and if you look at general force is your pressure, and there is a general displacement which can be through the dV, change in the volume, and the work will be basically PdV. In case of solid rod, which is elastic in nature, I mean like elastic, you can say elastic regime, then only we can talk of, that is the normal stress, right? So if you look at, that is basically normal stress and the strain volume change, then we can saw sigma n dV kind of things. And we have also seen the stretching of a liquid film, and which is with the surface tension force, right, per unit length, and then surface area comes into pictures, like and then we will get sigma s and df. Similarly, the reversible cell, the EMF E is being changed, and it is make this charge to move either to the from the cell to the outside, or the potential surrounding, or from the surrounding to itself, and we call it Ez, right. So now if you put it, you can put in a very general form, that is change in the work or the work done is equal to Fk, that is a generalized force, and dx is a generalized displacement, right. So if you look at, although we started with criticizing the mechanics definition of the work, but we are trying to assimilate like all the forms of work in this form, and which is coming within the realm of the thermodynamic definition of the work. So therefore we will be using these various modes of work. As I told earlier, that work is basically energy in transit, energy transfer in transit. It is not same as that of the energy, and also it is dependent on the path of the system, and unlike the energy is dependent on the energy is possessed by the system, and it is basically a point function, is a property of the system, and whereas the work is not a property of the system. So these are the things which we will be dealing with, and we will be looking at in the next lecture about the heat interaction, And as I told that in a thermodynamic system will be interacting with surrounding with the two modes, one is work, other is heat. So in the next lecture we will be discussing about heat interaction. Thank you very much.